Okay, good morning, everyone, and welcome to the second edition of Rhino Carbon Fiber Canada's CEC accredited carbon fiber and FRP workshop. We've got a lot of content to go over this morning, so I want to just do a couple of quick little housekeeping items. One of them being is if everybody can hear me okay and the audio is good, please give me a thumbs up in the chat group, or turn your mic off or unmute yourself and give me a okay. We're going to be switching over to the presentation fairly soon, and we're going to get this going. We got a lot of content to go over. So one of the housekeeping, thank you everybody that's giving me the thumbs up. That's great. One of the things about today's presentation, it's usually, and by virtue of COVID being still a sensitive thing and face-to-face meetings, which we're now kind of getting back to in some normalcy in the world, we tried our best to do more hands-on workshops where we're doing face-to-face, and we're going to be doing those again soon. The benchmark here is that you're going to get a lot of content from those hands-on workshops. Here today, you're going to physically see how we do things and how carbon fiber can play a big part in many of the applications that we do around the world, and of course applications that you'll see that are relevant to today's market. Just a couple of quick items. This is a CEC program, therefore at the end of the presentation, within about a 2-week period, for those of you who checked off, and we do have that logged in already, are looking for your CEC accredited certificates. You will be receiving those upon completion of the webinar today. So again, just a little bit about my background. I've been in the roofing, waterproofing, building envelope, concrete restoration, repair industry for close to 30 years now. I know I don't look it, but it is what it is. I maintain my age pretty good. So we're going to have, like I said, a lot of good quality content. I normally have a couple of start-stops throughout a 2.5, possibly 3-hour presentation, and within that time period, I'll stop and give an opportunity to ask questions. I usually don't like waiting to the end, because then sometimes people forget their questions. Or if you do have a question, again, head into the chat box, raise your hand, and we can deal with that on a one-on-one basis as well. And then, of course, I like to leave a good 15, 20, sometimes the last one was 30 minutes worth of a healthy discussion at the end of it. But certainly, by all means, during the presentation, which is rare, if there's something that catches your eye and you'd like to have an open discussion with regards to some topic, or even a slide that you caught that was relevant to a project that you're working on, you'd like to have an open discussion with it, then it's all fair. If you choose to have your video off, no problem. I'm just going to pick on you more often. Just kidding. But and thanks to Randy from Western Canada. I can see Randy will be picking on you a lot, so that's good. Thanks, man. Thanks for showing up. Appreciate it. But nonetheless, it gives us a great opportunity to review a lot of stuff here. The beginning of the presentation is kind of like a little holistic history of carbon fiber. We're going to talk about concrete a lot. We're going to talk about steel a lot, and where it plays with regards to concrete. We're going to focus on some residential. We're going to focus a lot on commercial, and then we're going to get into a lot of code compliances and where does the carbon fiber or composite materials world fit with regards to complying with all codes across Canada, United States, and abroad for all that matter. So we're going to, I'm going to switch now to the actual presentation. Once again, if everybody can give me a thumbs up or unmute yourselves and going, Phil, I can't see anything. And then we'll try and do a quick little reboot.
So good.
All right, it's got to pop up the presentation here. So can everybody see the presentation?
No.
That's not good. Let's try that again. Got some minor Bill Gates issues here, but we should be ready to roll now. Oh, now.
Yep.
Perfect.
Yes, we can see that.
Excellent. Thank you, folks. Okay, so for today's exercise, we're going to spend a lot of time talking about carbon fiber reinforced polymers. Basically, the acronym is FRP. You'll kind of see that throughout today's discussion with regards to what we do with regards to FRP and again where it applies with regards to expanding into the concrete repair industry and what that means. And sorry, it's got a couple more people coming in. So in order to understand where we fit in the matrix of the world of concrete repair, we have to look at feasibility assessments, and then we look at stuff like product selection, establish some design assist support, especially for our consulting community, develop a specification, and then, of course, with anything else, a quality control program. Now, sometimes that doesn't apply in holistically in the residential world, but in the commercial world, institutional and industrial climates, we do a lot in that area because it's critical to ensure that we're giving a real good quality repair in the end. So I used to say years ago that carbon fiber composites are relatively new to the construction industry. Well, I really can't say that anymore because we kind of been around, or at least the composite materials have been around for close to 30 years, 35 plus years. And although it had a primary function in civil applications, primarily along the Pacific Northwest for seismic retrofitting of bridge columns and large commercial projects, institutional type projects, as an alternative to steel jacketing. Now, while steel is still a prevalent reinforcement for concrete today, we're going to show today where carbon fiber and composite materials work for conventional strengthening techniques. We're going to spend a lot of time looking at case studies today where we'll use flexural shear and confinement reinforcing, utilizing all the variations of carbon fiber materials that are out there and the different strengths that they have related to and moving forward in those applications. So when we look at carbon fiber, we have to understand the composite of the material that we're looking at, that we're building with, and that's concrete. So what is concrete? Well, it's a composition of aggregates, a composition of the cement paste, and then of course the matrix that kind of pulls it all together is water, and the water portion that gives it its densification, it gives its ability to have binding to it. It's water ends up being actually its worst enemy in the end. But as we know, concrete as a chemical composition by unto itself is basically very strong in compression, but very poor in tensile. So in order to understand that better, we need to look at what that means. And when we look at concrete holistically as a building material that's used extensively throughout North America, what we have to do is understand what its actually range is. All right, so for some reason, there we go. So understanding concrete under compression and tension capabilities is, again, without any other byproducts, understanding concrete is strong in compression, but it's poor in tension. Well, what does that mean? Well, basically, when you look at loading a structure, which could be a beam, it could be a slab, whatever the case may be, or a wall, the compression portion is the top side of the actual slab. The tension member is on the below side. So that's where the concrete expands. And what's basically the common denominator to make concrete stronger, in essence, in order for us to build these massive superstructures we see being built along our coastal communities and our large inner cities? Well, it's steel. Steel is the common denominator. And steel, as a byproduct of high energy and high heat to produce all different types of widths, lengths, from 10M bar or US side number 4 bar all the way up to your large scale bars. Grade 60 steel is pretty typical, but this is now what takes concrete and puts it under a tensile, makes it ductile. So it's the steel that gives the opportunity to increase the size of the projects, the larger span bridges. Sometimes with bridges, it's post-tensioning cables as well. But steel is basically the common denominator that really helps build all these superstructures across North America. And the steel industry has done a phenomenal job in developing their types of steels. And now you also heard now the big market trend is towards GFRP rod, glass fiber reinforced polymer rebar, which is another big advantage in the industry when you want to reduce, if you're building in saltwater climates, bridges, or any structure that's in those areas that you want to prevent any type of corrosion setting in on these type of superstructures. But in order for concrete to be strong in some form of tensile, to give it some ductility, steel is basically the big byproduct now in the last 25, 30 years that we've been utilizing to develop that. And when we think of carbon fiber, we actually think of steel. So here's a classic example of your typical coastal communities and your large scale inner cities. When they're building with steel, you're using it to resist lateral forces, whether it's a wind environment or, again, the coastal communities are building around seismic. It's a level of understanding of what we do with steel to make it holistically work for these type of super condos and again, even bridges and whatever the case may be. And holistically, again, with carbon fiber, when we think of utilizing it in different applications, we think of how do we do it with steel. And basically, those are the same F prime C in every calculations that we use. And you'll see that throughout the presentation on how we can repair these type of superstructures. So now we'll talk about carbon fiber and how we relate to the world. So unidirectional, bidirectional, these are all terminologies you have to get familiar with when you're looking to specify or work with carbon fiber and understand its tensile stresses versus standard rebar. So that's why I always tell everybody, when you look at a project and you're looking to replace your typical steel plates or your steel jacketing, it's the same type of methodology you would approach from a calculation standpoint with, of course, different code compliances and other different formulations that we use to understand what we do with carbon fiber versus the tensile strengths of steel. So when you look at cured carbon, you can see that basically your typical 60 grade steel, with regards to us competing in the industry against steel, we really kind of start going off the chart. And you'll hear manufacturer reps refer to carbon fiber as 10 times the strength of steel. There's value to that, but we also have to put a cautionary tale and say that the higher strength, lightweight tension members that carbon fiber provide give strength to any one structure, but we are basically adding strength to an existing reinforced structure, or there are different ways to handle unreinforced structures. What we want to share with you today is what are the actual tensile strengths of cured carbon fiber fabric. And of course, the other product that's out there that we have is the carbon fiber laminates, which are pre-cured in a manufacturing facility with epoxy resin, and they come out to the job site in like large size coils, much like steel. Again, when you think of carbon fiber, you think of steel. So in our world of application with carbon fiber, we refer to it basically as a lightweight steel plate being used. So whether it's laminate or the actual raw carbon fiber that's wrapping a column or wrapping a beam, there's different types of applications that allow for higher strength carbon fibers and basically meeting the needs of the requirement utilizing just fabric carbon fiber. So there's two different animals and methodologies of approach here that we have, and you're going to see all the different types. But what is the matrix of carbon fiber that makes it so strong that allows it to be bond to any steel, concrete, or any structure? Well, there's the fiber, but then there's the polymer portion of it, which is the polymer matrix. So when we reinforce fibers, we're utilizing, of course, a high-grade, high-level strength epoxy to develop these different types of strengths for bonding to all these different types of reinforced structures. which helps create stiffness in our cured composite application. It's the polymer matrix. Without epoxy, we can't exist on any structure. So that's, if steel plate is an application, it's the anchoring of steel plates into a structure that's our epoxy, if you will. The difference being is you're not anchoring or firing different types of Hilti or high strength anchoring systems into a structure. You're utilizing the bonding agent, which is epoxy. And the nice thing about it is it provides environmental protection, and it's basically the most common polymer resin used for strengthening applications. But what are the benefits of FRP composite strengthening? Why would a designer or why would a contractor or anyone consider using composites for structural strengthening applications? First of all, they're lightweight. They're lightweight, I refer to them as lightweight tension members, and they're externally bonded to the exterior of any application that we're working with. As I alluded to in the other slide, and I'll show some testing that supports it, because we are driven by code compliances in order to do that, we offer high tensile strengths. The key one here too is low impact. Well, what does that mean? It's not only low impact to the client, but it's also low impact to the structure. So with many of our consultant community areas, it's important to have a level of response of what's it going to do to my structure. You don't have to factor in Hilti anchors on every steel plate. You don't have to factor any of that in, but what's the design loads? And those are the type of things we help develop with our consulting community, owners, builders, developers, and contractors. Conforming to existing shapes. Well, if I ever saw a piece of concrete that was pristine and clean and straight, we wouldn't have this as a benefit. So when there's slight undulations in the concrete or some deflection, whatever the case may be, the nice thing about the composite materials that are out there and that we utilize here with Rhino is it conforms to the shape, so you don't have to do massive grinding to get a structure or substructure flat. Fast installation, that's debatable. Everyone always says, well, carbon fiber, you guys are like professional wallpaper installers. That's fair. But in essence, it provides a QEW, a quick and easy way of application on many substrates, unless there's obstructions, conduits, and then, it's just a matter of how you get creative with the different type of composite materials out there to adjust to make conforming to those shapes. So jumping back to the last one and making the installation as quickly as possible. Cost effective. Well, I mean, everybody here is cost effective. It's something that is used prolifically throughout the salesmanship of any material, but it's relative to alternatives. So when you look at a 600-pound steel plate having to be scissor lifted to the underside of a slab or a beam or onto a wall, there's a higher degree of difficulty and a labor component that makes working with composite materials a lot more cost effective. The key things is that we're non-corrosive, we're alkali resistant, we increase the LCA, the life cycle analysis, to any structure. So whether it's a bridge or a large parking structure or the exterior of any parking garage above grade or below grade. And the other advantage is that we're creating new ultimate demand for that structure. That's the key here. Your classic example, and again, we'll share them in case studies, revolves around an owner who wants to add for example, a new mechanical unit to a rooftop unit, and it's 2x the weight of the old one. Those are all things that we can do to establish new ultimate demands to create, again, the next item is the servicing of the dead loads and live load demands on any structure. So this is just what we look at and what's been done over the last 30 years with carbon fiber and with regards to all composite materials is stress over strain. And that's what we typically do, the calculations for steel. What do we calculate our ultimate strain demand with dry fibers versus the composite materials? And the key line here is the gray and the orangey / red one. And the gray one is basically the ultimate demand of your typical steel and where it gets its ultimate failure. The KSI strengthening or KPA strengthening on the US side, when you look at that alternative and what you're doing, usually the carbon fiber wins the day and it's off the chart versus grade 60 steel on where it ends up as far as its final failure mode versus what the governing requirements are. So this is just over the 3 decades worth of developing that application of utilizing carbon fiber and where we stand versus grade steel. The other composite materials that you see there are e-glass or your typical glass fiber, and then aramid composite materials. But as you can see, carbon fiber really tips the scale high on its KSI strength over conventional. So what are the types of externally bonded FRP composite strengthening systems? Well, there's a variety of different fabrics that are manufactured. Most of them, at least ours, is involved in a dry layup application. We have our unidirectional. So unidirectional is basically the same language you would use in a reinforcement of longitudinal bar or reinforced bar in any application. So when you look at a beam or a wall or a double T or precast post-stranded bridge girder, they're all unidirectional type reinforcing or longitudinal strand or longitudinal rebar that's in a lot of these structures. So what does the carbon fiber manufacturer world does? They create a unidirectional or a longitudinal reinforcing, and we have them in a variety of widths to meet whatever structural element to wrap. And then again, our common denominator as a package is the saturant structural adhesive to bond those composite materials, and they're left to cure so they can establish the strengthening in there. The saturant is part of the structural element. And then we have bidirectional. The bidirectional is a weave of not only unidirectional, but a weave of carbon fiber going in the opposite direction, which adds both flexural and axial load support in a lot of specific type applications where that's required. But typically all these different types of unidirectional and bidirectional type materials, the common denominator is always epoxy or structural adhesives to bond them and weave them into any potential reinforcement application. And again, you'll see with Rhino, we have kits, we have different types of variations of widths. This is a 12-inch wide. We can get it up to 6-inch, 4-inch, whatever the case may be. It's all dependent on what's the requirement for the added longitudinal reinforcing to the existing structure for supplemental reinforcing. The other application is Rhino carbon fiber laminates. And the laminates are pre-cured. So in a manufacturing scenario, that epoxy, I'm going to just jump back to the other slide. The epoxy that's applied on site to these materials is already pre-cured in these laminates in a factory setting, which are a little bit thicker, so they have higher strength. So just so we know, the higher strength goes to the laminates, and they're used often in very pristine applications of undersides of slabs when you have long longitudinal reinforcing or long spans, if you will, that are required. And these coils are usually about anywhere from 50 to 100 meters in length and can be delivered to the job site in that form that you see above there. The important thing is that it's cut and cleaned with solvent. The epoxy paste is mixed and applied to the laminate, and then the laminate is applied to the structural element that the reinforcing is being applied to. Again, could be an underside of a slab, could be a long longitudinal wall. They could be used in axial reinforcing when mechanical contractors come along, and we'll show all those applications and openings of slabs and walls. So when you're looking at what type of composite material to use, again, the variation depends on its actual application. What's the compelling event that brought us to this reinforcing of these applications? Did the owner or the new leaseholder come along and say, I've got these, there could be a data center and they've got a new servers being loaded onto the slab that was originally not designed for the dead load that's being added to it. Can you imagine what this would look like if you had to do it with reinforced concrete as a concrete enlargement, that you'd lose massive height applications under, or even steel plate? Steel plate probably could have been done here, but again, you're using steel plate in a long longitudinal manner and then anchoring it into these underside of the slabs. There goes that impact. Low impact to the structure, easy to install, but most importantly, from a calculation standpoint, what's the method installation that works best here in the longitudinal direction of the reinforcing that's there, so that we can get a competent installation for the composite materials there, so that it relates to the loads that are needed. In exterior applications, sometimes it's just a matter of the structures deteriorating, and they want to use it more as a reinforcing to prevent any further damage. The picture on the far right, I'm assuming it's far right on your screen, is basically reinforcing an existing structure that was kind of falling apart, that required some tuck pointing. The blocks in this case were showing cracking. And again, we came up with an application for a corner wrap using unidirectional uncured, so this is regular cured material, to reinforce this area, and then subsequently the added material that would go over top of that, because it's an outside application, would be a waterproofing material, UV protected coating like an acrylic coating that can go over top of it to basically UV protect the epoxy, not the carbon fiber. The carbon fiber is inert, it's UV stable, but we need to protect the epoxy because that is the bonding agent in any application that's an exterior repair. So typically, again, jumping back to the laminates, the carbon fiber laminate world really did a nice job in their pre-curing of their application with how these are produced. And when you have long runs, it's really nice to work with the laminates, and they're pressed applied with the structural adhesive that bonds to it. And then you have to remove the air voids, pressing the rolls up against it and squeezing the epoxy out from both sides, and then flaring it back onto the underside of this application, directly over top of the carbon fiber, so you don't have to waste any material falling on you or onto the side. Typically, these structural adhesives are more like a paste, and they give high structural value. And again, in this case, with the engineered record, we help develop the lengths that are required, the spacing, and supporting the increase in the slab loads here. Another example, and this is actually a bridge girder in Ottawa, Ontario. This was just basically a holistic repair where they had a concrete beam that they needed to add load to because of some high strength issues above this actual rail overpass. And again, the laminates work very well there, but because it's an exterior application, and again, the engineer record had beam shear issues here where they had to increase the loads, and the laminates work really well here because, again, the concrete itself was pristine. There weren't any undulations. And again, the most important thing is we provided them a waterproof UV protective coating because it's an exterior application. I'm going to stop here because we still got a lot more information. Does anybody have any questions? By all means, unmute yourselves or jump in the chat. Okay, let's keep going. So what are the comparisons between fabric and laminate? Well, basically the fabric are all, they wrap around corners. When we're doing columns, you're not going to use the laminates around columns because, again, it's like a stiffened piece of steel that, although it comes out to the job site in a coil, very difficult to wrap around columns or any type of very difficult application. Typically, we have larger widths. The overlapping splicing is a critical part that we can have with the fabrics. They are lower material costs, so when there's cost associated, the laminates are a little bit more, and they act like a monolithic multi-layer composite. On the laminate side, again, they are pre-cured laminations. They do have higher tensile properties because it is a thicker composite material. They allow for quicker installation. Again, that's debatable for the contractors that have worked with carbon fiber before in the past. That's a bit of a debatable one. But the other thing that's nicer is it is a cleaner application because the actual materials come into you already pre-cured. So there's one step less with the laminates. So as we head into our code compliance portions of utilizing composite materials, one of the things we have to make, or what I make crystal clear is that we're a building add feature to any reinforcing of an existing structure. But what we can't ignore is what is required of us from a fire protection system installation. And if we are in a building and there are people above the building in a condo environment, We usually, and again, it'll range from, I'm sure the consultants in the crowd will debate me on it, but it will range from community to community. And this is where I say we develop code compliances from city to city, from province to province, by state to state, what actually those requirements are. And a typical 4-hour rating, we are typically going to fireproof any reinforcing, just like you would have with steel plates, over top of that reinforcing with a typical 4-hour rating, cementitious type spray-on application where the carbon fiber has to be prepared, typically lightly sanded with another primer layer over top of it. And then you continue with your typical cementitious type fire protection systems. Again, holistically, these are done a lot in typical underground parking garage communities or where we're dealing with living space or people above us. So that's important to know that from a code compliance, we know what it means to allow any type of FPS systems. There are intumescent coatings that apparently doctor a 4-hour fire rating. We haven't achieved that yet. We're more than comfortable with specifying what is the norm, but for all intents and purposes, this is typical, and we'll get into the code and where the code specifications meet that. But please understand that when we're doing carbon fiber or any laminate or any type of composite material reinforcing, we are going to comply with all existing local codes. Exterior applications where we're doing, let's say, a parking garage or columns underneath an overpass. In this example of confinement reinforcing of these columns that were just getting old and needed holistically a lot of concrete repair to it. But again, with regards to the DOT or MTO or transportation authorities, they have to have a protective architectural coating applied over it, but these are also UV waterproof protective coatings. And again, the key thing here is they have to be zero VOC or with respectfully a minimum amount of VOC in them or solvents, preferably water-based. And the key element there is because we don't want anything to deteriorate the epoxy. So let's talk codes. So within Canada and the United States, I'm referencing the Canadian side, but I'll talk about ACI a little bit as well too, is that we do have a governing body, okay? And because of the 30-year history and the amount of applications that are being used, utilizing composite materials to repair and give longevity to our bridges and longevity to our buildings, increasing their life cycle analysis, over the course of the number of years, and there's been committees after committees, both on the American Concrete Institute side and with CSA here in Canada, we have design building guides. So when you see a lot of the calculations I'm going to be talking about later, they're not just something I pull out pie in the sky. There are developmental codes that we have to follow for all intents and purposes. So does our consulting community. It's how we add and adapt different calculations to define developmental length for reinforcing of a beam or a wall or a column, whatever the case may be. And then separate to that is our Canadian highway and, of course, ACI highway bridge design codes as well. So in retrospect, all I can say is the composite material world just doesn't throw stuff against the wall to see if it sticks. We now have governing bodies that help consultants relate to certain applications. And more importantly, we are now code compliant as a structural reinforcing material. Here are some of the excerpts, if you will. Sorry, I couldn't say that properly. When you're looking at designing with FRP composite materials, we have specific codes in CSA, specific codes in ACI, and it's clear whenever any type of concrete, masonry, or steel component is being strengthened with as they refer to it, as a surface bonded FRP, all the check marks have to be going with regards to what is the supportive unfactor loads without any strengthening, and then how we add as the supplemental reinforcing to any of those structures. So this is important, again, for our design community folks here today, where we can actually pull that information off of and how it can adapt to all your different types of structures. Again, jumping back to the fire resistance. Holistically, again, we cannot do anything without our understanding that do we have to adapt from National Building Code compliances or ICC-ES reports, which Rhino has an abundance of approvals for, to apply all different types of coatings, all different types of fire fire-resistant coatings or systems, and what that means and what the relevance to the fire rating and safety requirements by all those different codes. Same thing goes for concrete members on slabs. Again, there's another section that talks about different excerpts and what they mean and where those strengthening applications apply for when it comes to those spread ratings. Highway bridge code. So again, from an ACI, CSI perspective, it's outlined. So, we have a certain factor of capacity that we're allowed to handle with regards to bridge girders or anything like, CPCI section or an AASHTO girder and what that means. And again, those code compliances are governed, and then we help and assist our consultant community or those transport authorities or DOTs or MTOs of the world to help design what that's going to mean and what the factors are that we can handle. So when you look at that and you look at all the different code compliances and stuff kind of doubles back to us and we offer our value engineering support, sometimes the calculations look like a calculus nightmare. But the important thing is that they're all documented now. So this is a derivative right out of the ACI code, which is grandfathered up here in Canada as well, as what does it mean to calculate shear reinforcing utilizing carbon fiber or composite materials. FRP reinforcement, its longitudinal strength, its tensile strengths are all little factors and equations that come into calculating shear reinforcement, flexural reinforcement. You can see the designs up top here that have to be shared and developed for any one application. So it's fairly intense is what I'm getting at here. And that intensity has to be done because obviously massive liability. We can't do anything no different than what the steel guys do for a 90-story building to design, a structural engineer to design a 90-story building. Those factor loads all have to come in from a steel perspective, and we have to do the exact same thing when it comes to the contribution of composite materials, in our case, FRP reinforcing, to help calculate that to make it work. So now where is FRP applicable? We talked about codes, we talked about, where does it come to play and what type of structures are we reinforcing, both from a residential, commercial perspective. Residentially, the basic is a lot of wall reinforcing and cracked slab reinforcing. But in the commercial world, it's, shear reinforcing of walls. We've done an abundance in the last 10 years of condition changes in a commercial building or an office tower where a new client comes in, and unfortunately COVID has caused a lot of departure in our owners of buildings from a leasing perspective, with a lot of companies working from home now or having their folks working from home. Our folks in the building owner development had to get a little more creative, and they've had to cut into openings because a client is demanding a new stairwell, a new elevator shaft, a new escalator for a retail environment to take over some of these empty leasehold environments. And just to go in there and do a concrete enlargement or a steel plate sometimes is not functionally sound. So in the case of number 2, you'll see this a lot in going through a post-tension slab or a one-way or two-way slab and cut that opening for a new stairwell or a new elevator shaft. How do you reinforce that with composite materials to make axial reinforcing work? Somebody comes along and damages a beam or an eccentric new load in the number 3 category here, and we're coming up with applications utilizing composite materials again, or FRP, to reinforce that beam or slab. Again, multiple axial reinforcing for heavier loads on top of slabs. And then of course, column reinforcing is a big one. And sometimes number 4 here comes a lot in even NewCon. We're going to show a case study of some failed low strength concrete scenarios in NewCon where our FRP works really well. Again, another application, door openings, a new client who's taken over an industrial building needs a door opening through a structural wall. How can we solve that with carbon fiber? And then of course, number 5 is your negative moment and versus the positive moment slab reinforcing on the underside. You have negative moment that we can do on top and carry loads through a wall or through any type of application of negative moment when we can't get to the underside. So I'm going to jump back to the steel now. So again, when you look at these massive superstructures that are designed today, or parking garages or infrastructure projects, it's nice to look at a diaphragm or an X-ray of what that steel potentially can look like. And when you look at it from a steel perspective, again, if I were to holistically look at this and say, okay, here's what we're going to do. We're going to do a concrete enlargement. We're going to do 4 longitudinal bars, not a grade 60 or number 4 or 15M or 20M bars, longitude in this direction to reinforce this beam or this slab with the stirrup details to create confinement. This is kind of what the methodology would be for that. But that, again, is engaging more load, more weight to these structures. And then at the end of the day, when we look at what we can do, so again, looking at all the steel's done, it's creating positive and negative flexural. In the beams and the stirrup details, it's creating the shear column confinement. Those are all the things the steel's doing for those existing structures. But we can do the exact same thing with FRP, right? So in a situation of a repair module or something with a whoops on any type of new concrete or existing structures, we unilaterally design these applications exactly like you would do adding steel to it. In a situation of a beam or a double T or any type of precast girder, we would U-wrap it. So it'll allow for not only flexural, but shear reinforcing. The confinement application, same thing. We horizontally wrap around a column to allow for that shear confinement to add strength as if you're adding steel to it. And then, of course, the application on top for a negative moment is utilizing carbon fiber straps or NSM rods, which are also made of carbon fiber. So where is FRP applicable? Well, not only do we use it obviously in reinforced structures, we use them in unreinforced masonry walls. Again, the design support is utilizing, again, unidirectional FRP in a vertical manner and in a horizontal manner to act like a beam. So if this were done in steel, you would see like large columns of steel or HSS columns going all the way up to the top and all the way down to the bottom, anchor plating, and then kind of holding that masonry unreinforced application. And then the key element here is that you don't have to worry about, in this case, it was a gymnasium wall that we reinforced with the wider application of the vertical unidirectional material to create more stiffness in that wall to give it the support that it needs. Now, in many cases, because this had a lot of deflection in it, retrospectively, it was done with a little bit wider material. And then we have underneath the window, which is a weak point in the wall, a horizontal strap going over top of it, acting like a beam there. The other application you saw before, again, unreinforced masonry walls with lateral cracks. Again, the design support is their unidirectional FRP with an acrylic-based UV protective coating, waterproof coating that goes over top of it, not to protect the carbon fiber, but more so to protect the actual epoxy material. So the finished look is this, but in retrospect, when you've got multiple cracks in a unreinforced block wall, or for that matter, unreinforced poured wall, most of the time something like this builds a cast in place or a poured foundation wall. It might have a couple of horizontal bars at the top and horizontal bars at the bottom, but then again, that's strictly for shrinkage cracks. They hardly ever put any, especially in residential applications today, any vertical bar at all. And then in this case, we're looking to stiffen and tighten that corner to prevent ultimate failure. So here's another quick little case study. This is where we used our bidirectional material in a commercial application. Again, it was found out afterwards that there was no reinforcement or the cores in this block wall filled in. So we came back and utilized our 4-inch bidirectional material, which added both flexural and shear strengthening in a horizontal vertical application. And again, we had to put a protective coating over top of it, even though afterwards they were coming with I believe it was not a shotcrete, but an acrylic type application like stucco to be finished over top of it. So again, unreinforced, reinforced, so long as we understand what the loads are or the exact loads on the structure, we can design whatever material to make it work within a certain tolerances. So there are limitations, and we'll talk about that a little bit later. But again, this is an application utilizing our bidirectional strengthening material for horizontal and vertical strengthening. So now the residential stuff. This is what you'll see other than outside of engineering that we do on commercial jobs in our applications of residential bowed walls. Again, both poured wall or the history, the 30-year history of Rhino has been in masonry construction and coming up with an application in residential deteriorated walls where we can offer design support, which is all online. All our information's online with regards to how you do the spacing, what are your calculations, and again, what do we do to anchor it? Is it good enough just to put the FRP plates, as I would refer to them, or beam, if in another instance, up and down? We have an application up here of anchoring into a sill plate. If there's not a sill plate, we have a way of putting a bidirectional strap along the top and then put the vertical applications in to act like a beam on the top, and then your beams, which are the composite materials, are submitted onto the wall, and then we have a shear pin connection, which I'll show a better detail on than you can't see here. But again, this is our unidirectional FRP vertical strengthening application for residential, and it typically, depending on what the bow is, if it's anywhere from, let's say, a 1/2 inch to an inch, we can typically do it on a 3 foot on center. But if it's more than, or sorry, 4 foot on center, if it's more than that, then we typically would come a little bit closer, and we'd have to do some adjustments with regards to how we handle any shear in the wall. So this is exactly what I was talking about. So this is all stuff that's on our website. And for residential bowing deteriorated walls, we have a certain spacing that's required, okay? And then your typical anchoring mechanism to anchor into the sill plate up at the top. And then we have different notable shear pin heading beyond into the footing design to shear pin the bottom of the wall. So you're really getting, again, no different than think of like an HSS column or a beam. That same shear pin is acting the same thing as you're going below the slab. If there isn't a slab, then again, we'd have to come up with a different application on how to tie that back in. But there are ways to solve bad slabs or deteriorated slabs in this shear pin connection at the bottom that allows for that FRP composite reinforcement to act like a beam. And again, the governing body here is whenever I get questions about residential, my big question is what's the height of your soil on the exterior of the wall? What's creating this bow? What's the hydrostatic pressure outside? Is it leaking? How can we waterproof it in conjunction with the structural reinforcing? And then get into the added value with our contracting community and our pro directs on how we deal with the shear and pinning connections. So now we're going to get into designing with composite FRP strengthening systems, and again, what that looks like. So where is FRP applicable? Well, when we look at structures, we look at what we want to do from increasing capacities and what are the elements that we're looking to increase. But it's the whereas that we're at right now. And we're looking at buildings, we're looking at bridges, we're looking at parking garages, chimneys in the industrial world, piers and wharfs in the industrial world. So your power and energy type clients that have aging and deteriorating structures because of a variety of reasons. Tunnels, both underground, above ground, and then pipes. We have a developmental application working on pipes, but holistically, it's anything from a 30-inch diameter pipe or bigger is great, because otherwise it's typically the other applications of the kind of in situ form type blow-in nozzle applications for smaller pipe works really well. So this is where are we applicable and where do we fit in the marketplace? Well, what are we doing? So in that marketplace we just talked about before, what are the structures? What are the capacity increases we're looking to upgrade? Well, columns, again, aging, or someone decided to add a load onto an existing parking structure. Beams, happens all the time in parking garage structures, increasing the stiffness or meeting new code compliances for beams if you're doing heritage restoration, if you're doing upgrades or new clients are coming in to add loads with servers and different equipment onto those beams and slabs. Walls, again, piles and pier caps, again, primarily in the industrial world. So what are we doing? So what are the elements we're looking to do to increase it? We're looking to increase the shear. In a beam scenario, in a slab scenario, we're looking to increase the flexural, which is in the opposite direction of the shear capacity. Seismic and wind application, again, for those of us that are in the coastal communities, looking at that. And, you know, I mean, everybody knows very well that the 100-year rain or the 100-year windstorm aren't 100 years anymore. It's happening on a weekly and monthly basis in many of our communities across North America. Our geology is changing, and the metrics of those codes are changing now to sometimes, even if you're in inner cities, you might be in a certain area that's specifically, you know, your regular class compliance coding, but then another area of that same city, you could be under a seismic D design class just because of the soil. So again, adapting to those different compliances and looking at it from that perspective is very important. Axial reinforcing is something we do a lot of. Again, new clients coming in wants to punch a hole through a wall or through a slab. How can we do that without disturbing the existing conditions and come up with axial reinforcing? Shear transfer and transfer beams, another classic one, and then increasing loads. You know, where someone's looking to add, you know, a structure to, again, a classic example is one of my clients, which is the Universal Healthcare Network here in Ontario. You know, they get an MRI unit that's 2 or 3x the weight of the old one. You know, a lot of low impacts required because you can't just go into a hospital and blow up their slab and pour a new one. You have to come up with different ways to come up with common sense applications to make that work. So for walls and typical crack repair, there are a variety of different composite applications. Again, with Rhino, all of these are on our website. But you know, there are more details that get a little bit more intense and involved with that. And you know, whether the big thing 30 years ago was a big part of our residential market in the last 10 years for composite materials. It's been, you know, applying it to commercial applications. And again, little different type of materials, little different types of resins. But whenever you get a block wall or retaining wall, slab repairs, internal or external applications, again, the low impact of many of these type of applications is composite materials because its capability to meet and conform to those existing structures, which really works really well. And again, from an estimating, for those of you who are estimators in the crowd, the nice thing about the Rhino packaging is that we typically, for all of these different repairs, have kits that work really well for one individual repair versus, let's say, a large-scale bridge, which would be a little bit more in-depth in a bulk package. So one of the newest products to hit the market in the composite material world is the crack lock material, and we've given a real long look at different applications, different composite manufacturers. Specifically here with Rhino, we came up with our crack lock, which is two little anode materials of glass fiber that are wrapped in carbon fiber to basically handle you know, anything from, let's say, a 16th inch to a 1/4 inch, anything that's let's say an inch or greater is probably not going to be a good repair for crack lock. But in your micro cracking of many industrial or commercial slabs, this works very well. So I'm going to switch to the video. If you can't hear it, give me a thumbs down or whatever. It should jump onto your screen fairly quickly. I don't know about the audio, but I think you'll get the gist of it.
He's pulling up a video.
It always makes me nervous. Betty looks like she's dead.
Oh, laying down, yeah.
But she's not like tucked in like this. She's like this.
I think that one's losing her mind a little bit.
Why?
She was playing with a ghost band.
All right, so can everybody hear me? Okay, sorry about that. I played this the last time and the audio didn't come through. The nice thing about the crack lock, it was designed and engineered to handle fairly significant cracking on top of slabs. I wouldn't really use it as a repair for wall cracks. I like our crack rock repair with our 4-inch wide or 6-inch wide unidirectional or vertical directional weave. But for on top of slabs applications where someone wants to put down a coating, high recommendations would be in the industrial warehousing type clientele, or again, let's say a garage that's got really bad cracking in it. But when you start seeing like heaves or potential shifting in a slab, that's going to be a whole different type of methodology approach. And for all intents and purposes, I would kind of shy away from utilizing crack lock for that. But for anything from, let's say, a 1/16 of an inch to a 1/4 of an inch, up to at least just under a full inch crack, you can utilize these. And then what we can do is design different spans. Typically, it's going to be 12 inches on center. You'll get 20 carbon fiber crack locks in one kit. So you'll be able to do 20 feet or more, depending on where you're going to start. And then again, it comes in a kit. So it's a really nice package that comes with it. But the important part here is that it's carbon fiber. So it's not, typically in years past, I would utilize, epoxy rebar, especially in a food environment or an industrial environment that's got a lot of like moving traffic with steel wheels and forklifts or any type of pallet jacking equipment. And, those slabs usually take a pretty good beating. And if they start cracking, like loading docks, for example, or again, classic example in our community of parking garages, it's usually the exit ramps that got a lot of hellacious cracking, sometimes due to salt, sometimes due to chlorides, sometimes just because the slab was under designed for vehicular traffic. The carbon fiber crack lock works very well to stabilize those cracks so that now when you go and put a traffic coating or a regular intumescent coating over top of it or anything that you want from a finished or vehicular pedestrian traffic scenario, allows for that crack to be stabilized and handle both shear movement and lateral movement from it opening up again. So a really unique application. And I would again focus primarily in slab repair and something that we can help design. But for the most part, again, the actual application, which is available on our website on our video trip, is available to you on a regular basis. We're into about an hour now, so I'm going to stop before we dive into the next hour worth of case studies and developmental and higher engineering applications for Engineering 101 for contractors and consultants. I'm going to open it up now to our community that's out there, so you can ask both questions in the chat or unmute yourself, and I'll do my best to police it. All right, Daniel, go ahead.
Thank you. Phil, I just have a question. You mentioned for the for residential, when you have foundation wall crack, you don't recommend using the concrete lock?
No, I know we have a little design thing here for a wall. I'll jump back to that slide. This is what I would prefer. So if there's a crack in, let's say, a poured wall or even a block wall, we actually have crack repair kits that are 6-inch wide that would add a lot more strength than spacing out of the crack lock. I personally think it's a little bit more cost effective. And most importantly, you're doing a bit of a stronger application with a wider bidirectional or unidirectional material.
Even if it's the crack is vertical, going all the way down.
Well, let's look at two things here. One thing that carbon fiber won't work on is a crack that's not repaired. So what I mean by that is, and we're going to jump into that very soon, is that every application of carbon fiber, when there's a crack in the wall, that crack has to be dealt with first. In the case of masonry, if it's a bowed wall, then of course we'd have to chip out the masonry up to a certain profile of bowing in that wall. But if it's a poured wall, you're going to see in my prescriptive methods moving forward, I'm going to demand that get injected with epoxy.
Okay, perfect.
So it's not going to be just good enough to do. And in this case, you can see in the slab, we're filling the slab crack with the structural saturated adhesive, which is important, right? So that's helping to create stiffness. The carbon fiber crack lock stitching in slabs is giving lateral displacement support so the crack won't open up anymore. On walls, Daniel, okay, if there's a crack in that wall, if it's a diagonal crack going up the wall or horizontally, then I'm going to ask that you inject it.
Sure. Okay. Perfect. Thank you.
No problem. Any other questions, comments?
Yeah, Phil, I have one. On that concrete crack lock.
Yes.
I quite like that product, and I understand the application that you're talking about in slabs and stuff like that. And what you just mentioned, you had the picture before you brought this up, that maybe you could go back to that there. And you were saying instead of crack lock, you know, the wall to the back here, you're saying let's strengthen that whole wall all the way up. I understand that application really makes sense to me, and as opposed to crack lock, you're just doing the immediate across that crack where the whole vertical face needs to be strengthened. Okay, but there's an application, let's say with a T-beam, where the whole vertical face of the T-beam, let's say it has a shear crack, it's only like 2 feet, something like that. Would that crack lock work in that application?
For a two, absolutely. So for a 2 foot, yeah. I mean, if it's coming off a corner and let's say you got, would it be a situation or a condition that's no displacement?
I'm sorry?
Is it a situation where there's no displacement in the wall, like the wall hasn't moved or shifted?
It's a crack. Let's say a T-beam with a crack, a typical classic shear crack, Phil.
Yep.
Where, you know, you could just put these crack, or what do you call them again?
Crack locks.
Crack locks. Yep. There every whatever, 4 inches on center, whatever the appropriate number would be.
Yeah. So 100%. Absolutely 100%. I got no issue with that. Absolutely.
Because I like the way you socket the ends in that, and then fill it, you cut the crack, you then put in the epoxy and then you socket it in there. That really is a slick way of doing it.
Absolutely, yeah. And it just comes from my 30 years ago of concrete restoration repair when I used to do it with epoxy bar. You know, even in a residential environment, mostly in commercial and warehouses, where we'd show up with, you know, like 20-foot, 15-foot lengths, and we cut them and we bend them on site and drop them in there. We use the same nodule aspect, except the little nodules that are the end pieces of the carbon fiber are actually glass rod. So we get huge benefit of it. And then what do? The smart asses that we were, we wrapped it in carbon fiber. So you get the strength of the nodule being glass fiber, and then the wrapping of the lateral support of a wall or primarily slabs to support it, to prevent it from opening up again. So it's to me, it's value in micro cracks. It's value in major cracks. They can be installed in 8 to 12 inches, whatever the case may be. It allows for a great and real solid repair job. And of course, as you see, you're flush to the concrete.
Yeah, it's great. So how long are those crack blocks? What's the lengths you can get?
So they only come in one length. Sorry, forgive me. I think they're 12 inches. Can Mike Tallarico jump on here? No, I think it's 12 inches.
Yeah, I'm grabbing it right now. Hold on a second.
Okay, how come they're only 12 inches? Because I need them 2 feet. Approximately, I think.
Well, how big's the crack?
Maybe an 8 that, and it's traveling at approximately 45 across a T-beam.
Okay.
Typical classical shear crack.
Okay. So what I would say to you is that if it's anything less than an inch, we're designed to be 8 to 12 inches on center. So you're hitting well below, as far as a 1/16 of an inch crack. It's parameters of what it was designed for. If it's diagonal, pay attention to how the diagonal crack's being dealt with in this picture right here.
Right.
Right.
That's what I would suggest in this T-beam application. Something like that. I really understand that. I would think
so what we can do for you is, and we do this offline, I love pictures. Pictures say 1,000 words. Send me a quick little case study, and within 24 hours, I'll come up with a snapshot for you.
Got it. Thank you so much.
Oh, no worries. Anytime. Great question, though. Thank you. Okay.
I have a question in regard to the masonry.
Yeah, go ahead, sir.
You tie that into the sill plate and you tie it into the slab down below. Will you be going into the details on how you connect those, or
The shear pin connection?
Yeah.
Right here?
Yeah.
Yeah. So there's a variety of different methodologies on how we establish the shear pin. Mostly what we say is you take a bulk portion of the leftover carbon fiber and you fill it full of resins, and you kind of cut the strands so you can turn it into like a shear pin, like you would a piece of steel, and basically drill a hole into the base or cut a hole into the slab, try and get it into the footing and create that shear pin connection. If you can't do this for whatever reason, the slab is heavily deteriorated, then like I talked about putting a longitudinal bidirectional material along the top of the masonry wall, I would also suggest you do one at the bottom of the masonry wall as well. And this way, then put your vertical strips down and you get bond here, and then you can probably set you can saw cut into the slab and create that bidirectional material tie-in, and then have all your vertical straps going in when you can't do this shear pin connection.
Okay.
Make sense?
I've used rope before in the past.
What kind of rope? Like glass fiber rope?
No carbon fiber rope. You just
great. Yeah. So you just bundle it all together, soak it in epoxy, and drop it in there?
No, we soak half of it in epoxy and then let it set up. And then
and
shove
then
it
you
in
let
the
it
hole
flare up.
because you
Yeah.
can't shove a loose fabric in a hole.
Real quick, Phil, if you mind if I interject, this isn't really, I mean, this is the width of a standard strap that you might put in a basement, but it's easy, just kind of just fold it like that. Leave about 6 inches at the bottom of the wall, fold it, and then take it and then just twist it into the peg. And then there's enough strength there when you twist the material that you can
Right.
stick it into the hole. And if you need a little extra leverage, just take from the injection gun and take that and just stick that in there, and you can push it in a little bit
Yeah.
from the epoxy.
But I know what the other gentleman's talking about. It's
Okay.
you can actually take the raw carbon fiber material, saturate it, and kind of just squeeze it together, or you can put elastic bands to tie it together. And the other part is just the raw material. It's like an FRP anchor, okay? And you drop it in there, and then you use the raw, and I don't want to speak for the other gentleman, but you use the raw material to flare it back into the strap while you dowel it back down. Utilize, it's almost like a stirrup detail with a steel bar. You're dropping it in there, and it's the exact same thing, Mike, except you're not doing the roll-up thing. You're just taking the raw material and then just cutting out the fabric that's holding it together, and you just squish it together and just kind of put it together and then drop it into the anchor. There's 100 million different ways to I've seen them all, and I approve them all, how to create that shear pin connection, but I would say they all work so long as you're utilizing it to sply it back into your vertical straps. Makes sense to me. Fair?
Yeah, it makes sense. I just wondered if you had something special on that. It's just a fancy drawing you got there.
So I do, but I do have one in the commercial world, and I'll talk about it, which is a prefabricated already, kind of like the laminates, an FRP anchor that's already got the hardened epoxy as a dowel part and the sply part that flares up to it. But we use it in the commercial world to carry a load through a wall or a beam. So we'll talk about that soon.
Yes, thanks.
Okay, so we're going to carry on. Hopefully everybody got another cup of coffee, and we're going to keep moving here. So one of the important things that we share, and again, it's not because we pull this out of our, it's our FRP installation procedures. And all of us share in the commonwealth of composite material applications because we have governing bodies that drive FRP installation procedures. And one of them that's important is the preparation of the concrete. Reinforced or unreinforced, what does that mean? And from our ICRI, our ICRI application, to ACI, to CSA, we have developed, and they've all been grandfathered, both in Canada and the United States and abroad, what it means to prepare the concrete in order to accept a solid repair with composite materials. Step one, of course, remove any loose or delaminated concrete. If there's partial depth repairs that have to be done, those have to be dealt with. You can do it with diamond grinders. You can do it with a chipping hammer, typically in many applications, but it's important to prepare the concrete prior to any strengthening material. If you're dealing, let's talk about corrosion for a little bit, because that's important. If you're dealing with corrosion or corrosiveness rebar in the actual application, it's important to detail how you're going to handle that. So it's not good enough just to get to the surface of the bar and it's staring at you as a complete little rust ball. The problem, as we talked about, if you remember back when I said about steel being the common denominator to make concrete ductile, is it giving its tensile strength and properties. The important thing is that once water, which is the composite material to make concrete, is its worst enemy afterwards, is supplemental the worst thing for steel. And once chlorides and salts and everything in water penetrate that steel, that's where you see the big delaminations, the big pops, whatever the case may be, for all intents and purposes has to be dealt with. So you have to treat the bar, get down to the rebar, but make sure, I call it a finger space. When you're exposing rebar in a full depth or partial depth repair, it's important to be able to get your finger around, I don't care the size of your finger, get your finger around that bar you're trying to reinforce. If the rebar is that corroded, get rid of it. Cut back to the point where you can find good bar, cut that piece of bar out, put a coupler on and add a new bar, okay? I'm sure my consulting community is applauding me right now. Don't make assumptions that the bar's okay, or you've treated it or you blasted it somehow, and you know, you got back down to good bar. If the bar is basically returning back to its iron ore state, do your client, do your owner a favor and replace it. If it's fine, if it's just surface rust, treat it, okay? Get the rust off there. Composition of muriatic acid, 5-to-1 ratio, or a cook little good hydroblast to get it clean, treat it, and then go back and do your typical concrete repair with your structural mortars. For what it's worth, Rhino has structural mortars of various strengths and compositions, and it's important to make sure the space between bar to bar connection you can wrap around in order to get an efficient structural mortar repair done. Again, here's a classic example. You got good clean bar, or you've added good clean bar, and you're going to trowel or pour in place in a full repair, full depth repair, your new structural mortar mix. This is all stuff that has to be done long before you can do any reinforcing. Cracks. Surface delaminations have to be treated. Anything greater than a 1/16 of an inch or 0.255 meter wide, which basically is a business card thickness, has to be treated. Okay, it's important that you deal with the cracks in any way, shape, or form. We just had a good open discussion about crack lock in a 1/16 of an inch scenario, utilizing it, filling that crack in, crack lock being a great application for that. But again, to reinforce and add strength in a added load scenario, we have to make sure that cracks are repaired. Well, how are they repaired? Well, there's a variety of methodologies. After the concrete's been prepped with an abrasive blast, so we can make the cracks visible, we have an epoxy crack injection kit or crack injection that should be utilized to bond and reestablish what I call the glue line. It's not good enough just to put a piece of carbon fiber over top of a crack or in a stitching environment. The crack has to be taken care of, especially if it's a through crack on an underside of a slab or in a wall. Why is that important? You have to structurally bond the concrete back together again. And over the last 30 years, with all the different variations of chemical composition in the epoxy world, that's the best common denominator to reestablish a glue line. What about if it's leaking? Well, we have variations, and Rhino has them, of polyurethane crack injection systems. You can inject directly into the crack if it's micro cracks or a very minor leak to create what we call a grouting application, or the bigger application is the one I prefer, is what we call the intercept low pressure crack injection solution. So if you've got multiple cracks in any one structure, a wall or a slab, we use these high pressure port fits and intercept the crack, okay, to create what I call a gobby water stop or a grout curtain wall, backside waterproofing to ensure at least close to 100% you're going to stop the water penetration moving forward. The key element here is when you're done there, make sure you're utilizing a structural mortar or an epoxy grout to fill the surface of that crack back in long before you put any type of carbon fiber reinforcing on it. So epoxy to establish and reestablish the glue line in a regular reinforcing scenario, polyurethane hydrophilic hydrophobic foams to create backside waterproofing with either low pressure or high pressure grouting. Why is that important? You'll end up with an ultimate failure. If you're assuming that the carbon fiber is going to span that crack and offer reinforcing to it without you reestablishing the bond line, you're sadly mistaken. If the concrete's going to continue to shift and move, you're going to compromise the FRP repair that you've done to it. So the methodologies are clear. We are following along with those code compliances and designs. And our ultimate prescriptive method is in any crack, as we know, and I worked for Lafarge for a number of years. Whenever anybody would call and say, hey, can you send me a mix that won't crack? I would always say, the only thing I can guarantee you is concrete will crack. Unless you want to pay $3,500 a cubic yard or a meter, whatever the case may be. But even then, I still can't guarantee the concrete won't crack. I can just give you formulations to minimize it, but ultimately, that's what's going to happen. Concrete cracks. And we have to deal with it in our structural reinforcing world. Prep. What is acceptable? What is not acceptable? Once again, it's not something that we just pull out of the air and say, here's what it is. It is a prescriptive method that's been developed by the ICRI Association, the International Concrete Repair Institute. It's been adopted by ACI. It's been adopted by CSA. Consultants all across Canada, United States, and the world will look at this and say, where do we design the surface preps? And typically, in any carbon fiber application of, let's say, slabs, walls, not so much in columns because they're basically typically contact critical because the strength of a column, the concrete is right out to the surface. But in many walls and in many slabs, because they kind of get worked a little differently from a contractor perspective, the weakest part of those concrete elements are typically the surface. So we need a good solid prep. And you'll hear different denominations of prep like CSB1, CSB2, all the way up to CSB7 and 8, which are really roughened, chipping hammer type applications. But for the most part, we're always going to call out a CSB3, which is basically like an orange peel finish. Classic example, you expose enough aggregate, you remove the latence of the concrete. We have our little chart variances, and most contractors that are competent doing structural strengthening have these so that if they're working with an engineer, they can show that the profile repair is prepped, ready for priming, and ready for a composite material structural repair. How do we do that? How do we get to an orange peel finish? Well, abrasive blasting, which could be sandblasting, dustless grinding with typically a shroud that'll allow for a vacuum so you can kind of create a bit of a dustless environment, especially if you're in real sensitive communities like institutional buildings, hospitals. In hospitals, I would probably recommend hydroblasting if you can, depending on the environmental cleanup afterwards. But water blasting is a very good application. Now, in many applications, we have to be cognizant when we're starting to blow stuff off the wall and we expose, like we have in the bottom here, some micro cracking. You want to be able to present that to your, because it may not have been seen before, but as you're prepping, all of a sudden you're kind of opening up a can of whoop ass, if you will, and you've exposed some areas that are cracking. It's important to make sure those are treated and are presented to a consultant or to an EOR, that they know that this occurred during prep. And then you can determine whether or not it's going to be dealt with from a micro cracking perspective with just a fill-in grout, or it has to be structurally injected. So typically in many applications of the composite material world, utilizing Rhino carbon fiber strengthening systems, we'd like to see a CSP3. And of course, a lot of times if they're just small cracks that aren't going through, the primers do a good job filling that in long before you apply any application. Now here's a critical one. And again, these are governing things that we add to our quality control and quality assurance. Moisture in the concrete, especially for those of you that are working in even potentially a residential home that's, you know, a heritage home or a home that's been built 100 years ago or 50 years ago, and it's got high levels of relative humidity and moisture in the basement. Make sure you have a moisture meter on you, and don't moisture meter the surface of the concrete that you didn't prep. Moisture meter the surface of the concrete that you prepped. And the reason why this is important, and I'll throw this out as a question, whoever answers it properly wins. What is the percentage that's allowable for you to apply any epoxy to any concrete structural element? I'll open it up to the floor. Okay, so I'll answer it for you and I'll win the prize. So when you're dealing with moisture in concrete as a sensitivity in your application, it's important to know and keep this under your belt that the concrete surface moisture content has to be 5% or less in order to apply any primer or any epoxy adhesive. Again, don't worry about the carbon fiber. It doesn't care. You can apply carbon fiber at minus 20-degree temperature. It's the epoxy that's the hypersensitive one, but it's also the epoxy that's hypersensitive to moisture. So if you're in an environment that's 5% or higher, it's important to get that area drier than that 5% content, whether you use blowers, whether you use heaters. And it's not good enough just to take a torch or a big high pressure air dryer and dry the concrete. No, it's the entire environment that has to be controlled to sustain that 5% or less moisture content in concrete prior to applying any epoxies. The reason being is if you shut that heater off or you shut that blower off, the moisture is just going to come back as you're applying that concrete. So make sure it's always running for at least a 24-hour period while you're working in that environment that's got high sensitivity of moisture in the wall. So once again, the critical path here is 5% or less moisture content in order to have a successful bonding adhesion for the epoxy. How do we apply? What are our mixing ratios? Well, the mixing ratios for our epoxies vary. We have 5-gallon, we have different size of gallon kits that are available. It's an A and B component. One's the strong adhesive portion and one's the actual liquid component. We basically mix those two components together, or we have pre-prescribed package kits that you can utilize to make it a lot easier for you to mix the actual components. And then it simplifies also your estimating process. But the nice thing about the bulk kits is that if you got a large job coming up and you don't want to play around and end up with arthritis or tennis elbow or arthritis from utilizing the cartridge guns, the bulk packages are really nice. You can get it all. You get yourself like a little painter spatula on site, and you mix the two batches together, preferably with two different spatulas in either one, so you don't mix them while you're in the pails. And then the important is to pay attention to your mixing ratios as per our prescriptive method on what that means, and apply the proper thickness onto the actual material, and then install it to the structural element, rolling out all the bubbles, and then press it firmly against the structure, flaring back any of the excess epoxy back over top of your carbon fiber laminate or dry layup application of non-cured fabric. So this is very important. Your mixing ratio, your consistency has to be there when you're applying it onto the structure, or to simplify it on smaller jobs, the cartridge sets work very well. And this is a classic example of a cartridge set kit for a bowed wall where you have 3 strips needed, whether they're 7 foot, 8 foot, or 10 foot, the static nozzles that mix and blend the materials, and then the anchoring bolt system that comes for your sill plate connections. This is a classic example of the Rhino carbon fiber bowed wall kit, but on larger projects, if you're doing a bridge girder, or if you're doing a underground parking garage or a repair somewhere in a more commercial environment, the bulk packaging of the 5-gallon pails is a lot nicer way to deal with larger scale projects. Here's just a quick little case study. I'm going to share kind of what we do and how we do it. In many cases, we get approached by consultants and engineers all across Canada, United States. And in this case here, this is a roof beam application where there was some cracking in one of the beams. Of course, immediately the engineer of record here, the consultant post-shored this beam, because the concern there was the micro cracking that was going off on a diagonal in this beam out to the outside wall, or potential column or corbel detail to the exterior. Although there weren't no additional visible cracking anywhere in the exterior application of the walls, it was primarily cracking in this one beam. And again, it wasn't really overly distressed just in that one area, but most of the other structural elements were fairly sound. When we see this and we get projects like this, it's very important for us to be prescriptive in how we're going to look at it and how we can share our methodologies with different consultants, building owners, or contractors that come with these different type of, hey, we started opening this up. This is what happened. What are your thoughts? How can we come up with a different way of handling this? But we ask more questions than we do normally in this type of case. So we want to understand what are the exact existing dead load and live load of the shear demands, potentially of that beam that was cracking. Can you give us an idea of the cracking? Now, I'm going to throw this out to the crowd again. This will be another question. Knowing that this is a roof beam and knowing that there is an eccentric load on the rooftop, including calculations of snow loads in the areas of where this project came from, is a concern.
We're gonna go to the golf course like last time, Señorita. Why don't you just pick them up there with the car?
Okay. All right. I'll carry on. I'm going to throw this out as a question. Knowing you see these as a roof beam or a beam on top of or holding a load of a roof, with these cracks, before prescribing anything with regards to potential added shear reinforcing for the shear demands on this beam, what are we going to do to those cracks? Question for the crowd.
You can inject them with epoxy, structural epoxy.
Congratulations, you win. Exactly. So, demo existing plaster on beam, prepped by ACI Co with a CSP3, making it bond critical, and then epoxy crack inject to reestablish the bond line of the cracked concrete beam. Right? Fair? So this is what was required of that actual beam and what the potential is to repair it. But holistically, we go back and say, well, there's a governing body that says from ACI code compliances, which work and are grandfathered up here, for shear reinforcing, we can U-wrap or just shear underside of that beam. But you know, the nice thing about the shear strengthening is that if we U-wrap it, we do a 3-sided U-wrap, and we're going to be doing a lot better shear strengthening utilizing our FRP unidirectional material to strengthen that. And that's just something that's in our wheelhouse to come up with that design. Now, in typical, it's developmental length. So how long is that beam going to be? What are the code requirements that are going to need? Because those diagonal cracks are heading back towards the wall or back towards a core bowl, the foundation wall, whatever or just a normal wall going up. You know, how do we do that? Well, those are calculations we come up with, coming up with different applications. It doesn't necessarily have to be the whole beam. It could be a meter beyond the beam. The cracks unilaterally will stop, let's say, in this area here. So we want to be a meter beyond that to add additional shear reinforcing it. And this is, again, we just come up with the application or come up with a solution, but we can basically fall back on any code compliances designs to illustrate how that application can be done. So it's non-intrusive, it's low impact, but most importantly, we're reestablishing the original design and dead load requirements for that beam. So this is the type of stuff when you look at, here we get a problem. Whoops. We come up with, the engineer record will come up with potentially what they're dealing with, and then we throw back a solution that'll work, that'll obviously be low impact, fairly cost effective for a repair without being massively intrusive, and then provide them eventually with a budget that works for both the owner and the consultant moving forward. So this is a typical example of what we do on a regular basis on more commercial projects. We do it on residential as well, on ones that are a little bit higher brow or have a higher degree of difficulty. But for the most part, anything in the commercial world, industrial world, we really do a good job of coming up with full-blown solutions. And we basically follow the prescriptive method that's out there for design and considerations. So FRP composite strengthening solutions, again, it can be a shear wall, it can be a beam, it could be column reinforcing, adding strength to a low strength scenario, positive and negative slab reinforcing. I think we talked about before about FRP anchors. And when we have a negative moment, when a slab is being reinforced on top, but the slab continues through into another room that needs to be continued with carbon fiber reinforcing, we have what we call an FRP anchor. And if the wall was here, for example, we would drill a hole through the wall, tie in the FRP anchor rod portion into the wall, and with an open sply material, feed that back into one of these straps here, and then basically use the epoxy to bind it, and then carry on to the other side, having a touch point. It's like doing a stirrup detail. When you're tying in stirrup details to connect longitudinal bar to longitudinal bar, you're doing the exact same thing with FRP anchors when you're doing a negative moment reinforcing on top of a slab, but you need to carry the load through because the slab continues through a demising wall. Or it could be a load-bearing wall for all intents and purposes. New construction is not off the hook here. In many new construction areas where we're dealing with, and everybody has a bad Friday afternoon pour, everybody has a bad rebar placement or misplaced bar in a certain area that's caught by our consultant community or the EOR, and they come back to us, in this case, multiple floors in a condo environment that required a 55 MPa strength for these columns in order for it to work. 28 days later, core samples come back and they reached a 45, 48 MPa strength. The genuine concern is we can't carry on with continuing of this superstructure while these concrete columns are low strength. And this could be in an old environment as well, too. You can get older parking garages and older above-grade parking structures that just at this point can't reach new code compliances, and you're maybe adding a new level to a parking garage. You need to re-strengthen these columns. In this case, it was a new con. Whoops. And again, it happens. Like I said, everybody has a bad pour day. Everybody has a bad, your iron workers have a bad day placing bar in the wrong location on a slab or a wrong location in a wall, and it adversely affects the strength of it and gets caught by the EOR. We can come up with the calculations to utilize our unidirectional confinement application for carbon fiber, apply it up against. And again, you can see we don't have to sandblast. I was talking about before about how strong columns are. The strength of the concrete with just an easy surface prep. It could be hydroblasted. It could be just a chemical, a low chemical washing of the concrete. We don't need to do, unless it's very pitted and the concrete's very poor, if there's a void, then we'd have to repair it. In this case, because these columns on 11 floors, 20 of them on each floor, needed to be wrapped in order to get back to the original intent design of the strengthening of these columns. But the important thing here is what I want you to take away, and it's a little bit glaring obvious, because these columns were on the inside of the structure, what did we have to do to them? That's a question.
Fireproofing?
Jackpot. Who said that?
Paul.
Hey, Paul. Thanks. Why do we have to fireproof it, Paul?
Code?
Yeah, 100%. I mean, that's absolutely the right answer. But remember what I said, they're inside the structure, right?
Yeah.
So they're carrying the load. So again, this is going to get some type of drywall, or it's going to be covered up with something, or, maybe they're just going to do another architectural thing. I hate to be the owner of the corner unit here, but whatever. At the end of the day, it absolutely had to be fireproofed. Yes, obviously 100% because of code compliances locally, but more importantly, because it's an inside column, right? So it's carrying the load of the superstructure. It's going to be carried up above it. But most importantly, from a code compliance standpoint, it had to meet that. So again, new con structures are not, they get caught up in a lot of nasty stuff. And a consultant does a walkthrough trying to get final occupancy for his building owner, and he notices that the mechanical contractor ripped massive holes through his transfer beam, which is holding up 11 stories in his entrance to the parking garage. This is not a poured concrete error. It's not a low strength error. It's a big whoops on the mechanical contractor's part for drilling these massive holes in this 2 meter by 1 meter by 2 meter beam, transfer beam, into a structure that weakened it dramatically. Now, how he got through it all to make these huge holes and the amount of steel that got cut and compromised, this one took a little bit more shear strengthening calculations to make it work from a URAP perspective, but and it took a couple of layers of fiber to do it. But most importantly, this was a carbon fiber unidirectional heavy thick fabric to allow it to be done. There were delaminations in the slab, I guess, which was a microcosm of the mechanical contractor causing certain damages to it. So all the delaminations had to be repaired. There were cracks in the beam over by the columns that were supporting it on either side. Those had to be injected. And then eventually we had to apply our CFRP 710 GSM unidirectional reinforcement material in both a unidirectional and shear reinforcing on the underside on the entire beam. So this isn't your typical axial reinforcing where we're just going to do it around the openings. No, this beam had to basically be completely reinforced from end to end. And that's exactly what happened in this application in order to get it strengthened enough to carry on. Now, notably, is this a site super error? Is this a consultant error? I mean, at this point, it doesn't matter. It's a matter of coming up of what works from a calculation standpoint to get it done. But again, here's a question for the crowd. What has to be done on this transfer beam on the underside of this entrance to the parking garage? What's the final stage here?
Fireproofing.
Yeah, so absolutely had to be fireproofed, right? If this
Yeah.
was done with steel plate and steel plate was being anchored into this and wrapped around it, it absolutely would have been fireproof. The problem with the steel plate is what do you think the height restriction is here in the entrance of this parking garage by a code compliance? If we would have had to build that up with steel or built it up with concrete enlargement, would it have worked?
Probably not. Hey, Phil, I got a question. When you, earlier in your presentation, you pointed out in the code that in order to apply strengthening using FRP, the beam would have to at least be able to carry the unfactored loads. I think I'm correct on that, right?
You are correct, yes.
Okay, so this one, those are flipping huge holes in it. Is there it almost seemed like it wouldn't be able to carry the unfactored load here. Is there a bypass around that part of the code, or am I missing it?
Yeah, so the engineer of record here was able to come up with the existing load of what it was designed. So above this structure, above the parking structure, and this was only a single level garage, was 11 stories. So they had to come back with the new factored loads of this to create the demand of what we were going to do for it in order to get it to the original demand. So thank you, mechanical contractor, for compromising the transfer beam here. But at the end of the day, the engineer record provided us what we needed to get, and then we were able to calculate to get it where it is. So where it is now is basically it's at its unfactored load.
Okay.
Give me, my screen is frozen. Can everybody still see the same slide?
Yeah,
Okay,
I see the same slide. Oh, now it
Okay.
changed.
Okay, here we go. So in many existing structures, and again, it could be new it could be retrofitting of new conduits for a hospital or sending new pipes and new mechanical equipment through a slab. This is more of a positive moment reinforcing. So this was basically an apartment building that was getting all new brand new equipment from the basement all the way up to the roof line. So every slab that, again, mechanical unit or the mechanical contractor had to, and this was a preventative prescriptive method. So this was being known in advance of what was going to be required, what size the openings were going to be required for the plumbing stack or any type of new sprinkler system, whatever the case was. And what we did here is we understood what the existing demand was, what was going to be required, and what the axial reinforcing was going to be needed. In this case, we needed a higher strength material. Can anybody tell me what material this is? Is this dry layup or is this laminate?
That is laminate.
Correct. That is our 4-inch wide pre-cured laminate, higher strength composite materials. And the reason being is that when you get a cluster of openings like this in one area, the factored load here is already compromised. So we have to understand in which direction the existing reinforcing is going, and then create an axial design so that entire area gets stabilized beyond the openings itself. Does everybody understand that? Precast bridge girders, CPCI section. Another classic example where carbon fiber or composite materials work very well in this application. Now, when this happens, and the big whoops here is that, you know, a truck larger in life can't go underneath an overpass and causes this type of holistic damage to an AASHTO girder or a CPCI girder. You can notice here that it's not just the regular reinforcing that got damaged, a strand got compromised here. These post-tension strands that are in these AASHTO and CPCI girders are very important for the vehicular traffic and the loads that they carry on these aging bridge structures. In this case, this was a massive amount of concrete repair. In the case of the strand being compromised, it had to be cut back, and then similar to in the wrestling world where you see the corner turnbuckles, the mechanical contracting, or sorry, the rebar contracting world have the same type of turnbuckles that would be put on each end and a new strand introduced to strengthen this area back up again. The other strands weren't as damaged. Some of the other bar was bent. You know, some of it got replaced. Some of it just got reconstituted. But the important thing here is before we do anything else here, we have to reintroduce new reinforcing. We have to reintroduce concrete, a high 75 MPa structural mortar grout to pour and obviously break back in an area that we can get back to good concrete. To reintroduce any of this to carbon fiber with a U-wrap again, up and around for shear and flexural strengthening, going back in about a full meter. And of course, the scary thing here is the Ministry of Transportation or DOT is not shutting down the bridge for you. You'll get a one-lane closure operationally to get it done. And of course, you're going to get different temperature variances. So again, we had to do a confined area to close it off. But then at the end of the day, when we were done, we did our waterproof protective coating. Here's a classic example. Does anybody know why we left that opening space between all the U-wraps after the concrete was poured? I'll explain why. The reason why that opening was left there is because this is in around the area where we introduced the new concrete pour, where we broke everything open, opened it up, fixed all the reinforcing and reformed it. We're allowed that opening to allow it to continue the concrete to cure or dry out. We got our high strength requirements that the EOR allowed us to continue with our URAP application and reinforcement in those areas. But this is the type of hoarding, even though, you know, it wasn't done in the dead of winter, we still had to make sure we had perfect ambient temperature for the application of our epoxy to ensure a quality repair and to make sure that the concrete is still allowed to cure and dry properly, and then eventually introduce the final stage, which is the architectural UV protective waterproof coating.
Hey,
So that's the
Bill,
final repair there.
Bill, on that bridge there, you don't have to wait for that concrete to cure 28 days. Rather, you measure the moisture that it's less than 5% and you're good.
Jackpot, yes.
Okay, and that goes with a grout repair too. So if you're going in, the first thing you're going to do is to reinstitute the beam. Well, take off the latents of it,
Yep.
at the cracks and that kind of thing. And then you've got to wait till you're at the 5%. Then you can go and do the FRP.
Yeah, and here's how we sustain that. See this containment area? We didn't want exterior elements to affect our moisture content. We wanted to maintain a certain temperature variance throughout. Most importantly, while we were doing that, to get it to the point where we can apply the carbon fiber and not wait 28 days to go back and reestablish lane closures and all that. And so we kept this internal environment exactly the same for 24 hours for 10 days. So let's talk about what do we have as far as control and assurances that everything that's being done. Oh, sorry, we got a quick question and I'm going to answer it right now. In this case, did not the DOT require a fire rating on the underside of the bridge beam? No, because it's an exterior application. So this coating, although it has a 2-hour fire rating, in our case, DOT or MTO only required a UV waterproofing protective coating over top of it. Dimitri, I hope that answers your question. So for control and assurances, again, what is the governing body? And this is all done through third-party analysis. How can we ensure that you just received a quality application? Well, again, we're governed by another governing body, whether it's ASTM or CSA, everything from an ASTM perspective. What does it mean? What is a procedure for pull tests? What's an adhesion test? Again, over the years, this is why I say, and predominantly from a code perspective and compliances, that typically composite materials are utilized in applications that we follow certain prescriptive methods, and this is one of them. So when we look at testing parameters, we want to make sure there's a certain ambient temperature. In case of that bridge, we had a certain ambient temperature for the 10-day period that we had to maintain moisture control, to maintain certain temperatures, and that was all driven by the epoxy in and of itself, and of course the concrete as well. Adhesion tests, what are the parameters? We have certain puck tests that are done to pull material off a wall that has to reach a certain gauge or requirement, both from an MPa and PSI strengthening perspective on the US side. And then what's the performance levels to have a representative do mock-ups, and that are typically in the area of the FRP installation, or sometimes right in the actual FRP installation. So for tension tests, we take samples of our material. We do this on a regular basis. This is to ensure our quality control from an internal perspective of the tension tests we do, so we achieve the proper tensile modulus, the strength, and that right goes back to what we talked about again, stress over strain. We have to make sure that our raw materials are there. And then the ones that get done on sites are adhesion tests. This is critical because we have to have a level of understanding that the installation was done properly. And this is primarily in a lot of commercial applications that's expected of not only to meet the prescriptive method of the installation, but did the installation meet the requirements of adhesion with these pull tests before and after the installation. Typically on job sites, we'll set up a little test panel like this, off and away from the actual repair. And these little saucer pucks are done with this ASTM equipment to do the pull test and make sure we're pulling concrete with the fiber. That's the critical part. Sometimes we go and EOR will ask us, I want a sample right out of the repair that you've done. Easy to go back and fix that, but again, it's critical to ensure that these pull-off tests are meeting the cured carbon fabric installation methods that were driven by the minimum standards for adhesion tests. And this is typical what we'd like to see with those saucer pucks in conjunction with the carbon fiber is a nice chunk of concrete that comes along with it. Not that that's because, sometimes we get erring reports. Sometimes that concrete's weak, right? But the pull adhesion test tells us whether or not we did a good job in bonding. I'm going to stop here for a quick second because this is kind of important. With regards to designing, strengthening, and understanding testing with carbon fiber composite materials, does anybody have any questions before we go into the development side of the business with carbon fiber? So these are all things that we can provide you. So again, for our consultant community that are here on the call today, I can provide you all the direction and the details on what and where those various tests that we need to meet in order to comply with structural strengthening, adding demand and loads, utilizing composite materials. When we look at carbon fiber composite materials, and we talk to a lot of building owners, what we want to do is talk about what is your repair cost versus time, and what do we do to extend the life cycle strategies of all these superstructures that we're trying to rehabilitate. And for all intents and purposes, homes, old age homes that, people have never done anything with the basement before, and they go in there, they want to do the basement, and now they're finding out all these methods. It's important to look at all these structures. And initially, from the preventative maintenance standpoint, if you wait too long down the repair phase strategy, then you end up with full-on replacement. Those dollars become exponential. And as you can see, the dollar amount becomes huge. And the critical thing is that all these structures are designed with concrete. And there's a ton and a million different prescriptive ways to solve concrete early on in the stages of preventative maintenance that don't end up giving you massive high costs 30 or 50 years later, okay? Because replacement cost is massive. So carbon fiber, in essence, is a preventative maintenance repair where when you look at any type of strategy you're taking on or any undertaking you're taking on, residential, commercially, industrially, it's good to look at it because, listen, when concrete cracks, don't wait till 20 or 30 years later. And I'm talking to you like I'm talking to building owners, because I kind of get anal with them when I look at their preventive maintenance things, because I like to prevent things like Surfside, Florida. I like to prevent things like what's happened in Montreal with a lot of their bridges that they let go to 50 years that are now falling apart. And now Infrastructure Quebec is spending billions in the holistic replacement now of many of their bridges. Our biggest eyesore in Ontario is the Gardiner Expressway. Thankfully, over the years, carbon fiber has finally made it onto the palette out there to repair many of the underpass scenarios there. But I mean, it's a situation where it could have been prevented a long time ago. So if we get into the early stages of repair and utilizing composite materials, you're really doing a great job of extending the life cycle strategy on your building, on your superstructure, on your concrete elements to prevent the massive costs dealing with repairs or replacement. If we stay, and building owners and governments stay within this holistic category of preventive maintenance and repair phase, you prevent full-on repair, full-on replacement down the road. But we just finished talking about cracks. Cracks are always a big indicator. This is a brand new structure. It's a double T beam on an exterior parking structure. And how do we handle beam shear cracking? Well, as you can see, just like that roof beam, this double T that is on the top level of an exterior parking garage had a diagonal crack that went all the way to the exterior column. And what happened? What caused this? Well, good old human failure. Again, when a contractor or a landscaping contractor, or in the Great White North here, our horrible snow removing contractors decide to load or overload a certain portion of the parking structure or whatever, in this case being a parking structure, what happens in situations like that is when you overload that area, and preventative maintenance would have been, if they would have talked to the consultant, if they would have talked to the owner, they probably should have sent it somewhere else. They overloaded that area of the beam for whatever period of time. The crack appears, and then now you've got a load issue in that area where the crack has come into play and has to be dealt with accordingly. And because this was a relatively brand new parking structure, it wasn't designed for this, accepting this type of load. And of course, he overloaded it right at the edge, caused this diagonal crack. It was caught in time. Let me repeat myself. It was caught in time to prevent any post-shoring requirements, but we were able to come up with the same similar methodology we did with the roof beam to come up with carbon fiber to detail the repair costs and the time curve strategies to get this back into a reinforcing of that double T and get it back into service. So this was strictly an FRP shear and flexural reinforcing for that structural element and reinstated. And again, just a typical, this is a cementitious coating that was applied on here to kind of mimic concrete, and also gave it For whatever reason, they wanted an additional 4-hour rating. So we had a cementitious waterproof coating put on there that was UV protecting. But most importantly, the beam was put back into service and this area was put back into service so that they didn't lose any critical time and or parking stalls. And you can see we basically worked within a confined area of the area that we needed to do the repairs and get the developmental length that was required of us to get that double T back into joist back into shear upgrade.
Phil, excuse me, Phil, can I
Yep.
ask you on that particular type of repair, do you come and push that crack back together at all? Is there any sort of a unloading of that beam that's required, or were you just fixing the crack and leaving that, what's a small deflection, the shear deflection in place? You just leave that in place and repair it right there, and that's it. There's no pushing it up back in place or something like that. What's your experience with that?
Yeah, so no need for that. It was less than a 1/16 of an inch crack. But the concern there was we didn't need to shore post it. We didn't need, I mean, obviously the contractor just didn't abruptly leave that load of soil there. He had to get it off of there. So the added vibrational equipment that he used and everything else opened up cracks on the other side as well too, but it didn't show any displacement. So the good news is we were able to chemically inject it with epoxy.
I see. Okay. Got
So
it. Thank
classic
you.
prescriptive method. It's still a crack. A crack is a crack is a crack. In a structural member like that, we're not going to let it stand alone. It has to be the bond line has to be reinstituted with epoxy, and then we can get to this.
Got it. Thank you.
Now, could it have just been solved with an epoxy? Probably, because there was no displacement, but the engineer of record wanted a backup, and this is the backup. So shear cracks and shear failures. Whenever a slab or a beam gets overloaded, case example, and it happens in new construction, if you don't have a pre-development plan of loading a new construction application with an engineer record that can schedule and let builders, developers know where to load slabs with lumber or steel or whatever other type of pipes, whatever comes to load a structure. When they don't understand the abruptness of a shear failure that can be caused by this, what happens is that sometimes you get ultimate failure, especially in the concrete. Remember, concrete, strong compression, poor in tension, but the only common denominator is the steel. So most of the time, you're going to have your steel that gets compromised in these shear cracks or goes full tension. And then we have to, and so I believe it was Daniel who said, hey, Phil, didn't you have to do anything in advance of that crack on that other beam, that double T? We probably, in this scenario where we saw multiple shear cracks appearing, we would have post-shorted, okay? Because we don't want any additional punching shear failures, because then you'll get ultimate failure. There's absolutely nothing carbon fiber can do in that scenario, okay? So when you get full failure like this, it's a scenario where it's going to be a re. An engineer has to be alerted right away. A consultant has to be brought on board. Shore posting has to be done. And then subsequently, if there's this much deflection, you get ultimate failure. If it's a lot more cracking or bigger cracking that occurs, more in a deeper, like through crack, it still can be dealt with. It still can be rehabilitated, but most certainly a consultant has to conduct a post-shoring diagram to make sure that the building is going to hold up. Why is that important? This is why. This is a punching shear failure caused by corrosion. Concrete's number one enemy, and obviously steel's number one enemy. So when you look at a scenario like this, it goes right back to that diagram I showed before about a lot of preventative maintenance can be dealt with accordingly if owners will take responsibility and developers will take responsibility of a good preventative maintenance program that prevents all this from happening. So again, ultimate failures, Surfside, Florida, parking structures like this, bridges that end up falling in, potentially killing people, whatever the case may be. It's easy to pick what those methods happen, what happens to prevent that. Corrosion is the ultimate. cracks when you're looking at preventive maintenance and doing feasibility and condition assessments are important to pick up on, and they can't just be left to pass, because this is ultimately what happens. So this is why composite materials work well to extend the life cycle, to extend the perpetuity and profitability on parking structures and buildings and bridges, to extend that ability so you don't have higher replacement costs down the road. So what differentiates us, i.e. Rhino? Well, over the course of the last 30 years in the industry, Rhino's done an excellent job on the residential side. In the last 10 years, we're doing a better job and continue to do a better job on commercial, but we offer now design support, shop drawings, and ceiling drawings when detailed for any application in Canada, United States. I spend a lot of time with building owners and contractors across Canada and the US on virtual calls sometimes to do condition assessments and FRP feasibility support. What does that mean? Well, FRP sometimes is not the answer, right? Sometimes it may very well be a steel jacket. Sometimes it may very well be a concrete enlargement solution. Sometimes it might be a post-tension solution. What we want to do is create, and you can see in our little skew here of everything that we do, if it's a steel solution, we should be able to do it in carbon fiber. If it's a concrete enlargement, we probably can or can't, but it depends on the impact of the structure. And most parking structures, you can't enlarge the concrete because you're removing parking stall feasibility, which hurts owners. So those are important. The other thing is that we provide budgets. We do estimates for FRP solutions via our ProDirect program. We work very closely with our ProDirects, and the applicators that are here today are usually fairly savvy to provide, if I provide them the solution, they provide the full-on supply and installed. So we work in conjunction together. The big thing here is that we're not ignorant to the fact of understanding local codes and labor laws. So it's not just great that we threw out and share with you today all these ACI and ICRI prescriptive methods, but we also have to understand the labor laws. Sometimes there are certain restrictions with regards to that. And again, most of it boils down to the environment that you're working in. If you're in a hospital, you have to do certain things. If you're in an underground parking garage, or if you're in a tight confined space, you need to be confined space certified, all that type of stuff. This is the type of stuff we do typically first quarter of every year, and I do independently with consultants and engineering firms and even architects for all intents and purposes. We provide technical training and technical support to all industry pros and consultants. Inevitably, our Carvis Arboretum is we want to make sure the engineering works and that our Rhino FRP reinforcement strengthening system is installed correctly. This is a live link to our commercial website. I'm not going to click onto it. You can do that at your own leisure at www.rhinocarbonfiber.com. But basically, our biggest advantages as we look at the repair, the strengthening methods that are out there, reducing life cycle costs, but increasing life cycle analysis to the transportation, the equipment and labor costs. Our responsiveness, I think it's second to none, and how we can do and what we can do to help resist shear, flexural, and torsion forces in any structure. Sustainability, of course, that's a big thing. Sustainability by design, sustainability by life cycle, and how we can do to increase any type of structural member out there. And our availability. We have availability with our headquarters in Mississauga, Ontario, and in Michigan throughout our representatives around the transcontinental US. And again, we work with local contractors to train them with our Rhino carbon fiber projects throughout North America on our commercial and residential installs as well too, because sometimes they can get sticky. And we work with you on a regular basis on that. Within our billywhack of materials, we have our bowed wall repair kits, crack repair, corner wall, crack lock, which is the material we showed in the video, accessories, which are like the guns, epoxy, urethanes. We have bulk carbon fiber for the large commercial jobs. And just recently, we've introduced structural mortar bags, which are of high MPa, anywhere from 75 to 85 MPa, high strength, can both be troweled on, can be poured, and can be formed into any irregularities on any structural repairs. All right. That adjourns our meeting for today, and we'll open it up for questions. No questions?
Bill, I don't have a question, but I have a comment. Thank you very much for this workshop. It was very informative. You did a great job of it. Really appreciate it. And we'll be in touch regarding some of these challenges we come up with. Come again.
Oh, outstanding. I believe that's Phil Dorn, is it?
That's correct.
Outstanding. Great. How are things in Brandon, Manitoba, sir?
We got a whole bunch of snow, so I'm a snowmobiler, so the best weather forecast for a snowmobiler are 3 words: severe storm warning. And we got that, Phil, so I'm happy.
There you go. Yeah, just do me a favor, Phil, keep it there.
Okay.
I don't know what's going on here in Ontario, but we're tropical weather right now. So I'm gonna put my baseball hat on and go for a walk in my shorts.
Yeah, wonderful.
Yeah.
Okay.
Anyway, so just last housekeeping item. Within the next 2 weeks, you'll all receive your CECs. For the contractors in the group that want their CEC, their 8.5 by 11 wallet certificate or a wall certificate. Reminder, if you also want your wallet card, make sure you send me a note so we can get those out to you, as well as the CEC certificate. Thank you, everybody. If anybody wants to talk to me offline, by all means. We just about hit our 2.5 hour mark. And again, I'll open it back up for any last minute questions, but thank you, everybody. And looking forward to working with all of you in the near future. And if you want to double back, we still have another one on March 14th and March 28th. So just FYI for that, if there's something that maybe you missed or you'd like to kind of double back with us again, you don't have to worry about receiving your CEC again. You'll get it from today. But for all intents and purposes, yeah, thank you, everybody. And I'll open it again for some last minute questions. Okay, well, thanks, everyone. Oh, go ahead.
Are the other dates going to be the same content? You just are doing multiple dates, or?
Yeah. So it's going to be the exact same content, but if you want to jump on because there's something that maybe, I have a propensity to kind of blitzkrieg through a lot of stuff, and I like to, if there's something you wanted me to focus on, we can do that independently offline. But if you want to jump back on the 14th or 28th, by all means, you'll get your certificate from today anyway. So absolutely, yes.
All right, sounds good. Thanks.
Okay, thanks everybody. Happy Thursday. Have a great week. Stay blessed, and we'll talk to you all soon. Thank you.
Thank you as well for your time.